So starting unit 2, work or energy and momentum. So we'll build on what you did in grade 11. Work and energy is where we'll start with this one, or kinetic energy. So I'll just talk about work first and what that is, a little reminder, hopefully. That work is, technically we define it as the force times the distance that something moves. But to be really picky about it, we say that it's only the component of the force in the direction of motion. So if you have something like a person here pulling a block at an angle, but we assume the direction of motion, right, is straight like this, right, then we only consider the component of the force that's parallel to the direction of motion. So that would be this here, this F cos theta, which we obviously get just by multiplying it by the cosine of whatever the angle is. And so that's our lovely equation. Defining it, more than that, or thinking about like what is this? It's worth noting, as I wrote in purple here, that it is a scalar quantity, right? It doesn't have a direction, even though we're very picky about the direction of the force, right? That it has to be in the direction of motion. But like, really, what is it, right? To say that somebody did work, right? Well, basically, you're saying that there was some force applied and that the thing actually moved, right? Something is not in the position it was. Otherwise, no work was done. And that gets us to just building off the math, right? That gets us to positive, negative, and zero work. So negative work occurs when the direction of the force is opposite the direction of motion, right? So if you look at this picture here with the person and the dog, you can see, I think this force here, the one that's actually shown on the dog here, I'll be a little more specific about that. This is showing the force of the person on the dog. So presumably anyone who's like me walked a dog that's kind of pulled you along a little bit and you're trying to resist the motion, right? You're applying a force in the opposite to the direction of motion. Thus, you're doing negative work, right? The thing is moving, but you're actually impeding it. So it's kind of a bit interesting in that regard, that it's negative work. And this here, the other one, represents the force that the dog is applying to the person. And since they're moving in that direction, then that would be positive work. And it's kind of an interesting situation like that, because it really, if you look at this, it sort of balances out, right? The person does negative work, the dog does positive work, and the net is kind of zero. So you have to be careful about when you use these equations, or what you're actually getting it for. And then, of course, a very important one always comes up on physics tests: zero work, right? And zero work occurs when there is either no force or no displacement, right? Either or, anything that makes that equation equal zero. So you could have a person over here pushing and pushing and pushing, but if that thing's not going anywhere, right, then no work is being done, right? No matter how much energy they're using up by pushing and pushing on this thing, there's no work. Similarly, if something is moving, but there's no force being applied to it, right? It's just an object moving through space at a constant velocity or whatever, then, right, no work is being done. Well, let's look at a practical example here. A girl pulls her brother in a sled. So the combined mass, this would be the combined mass of the brother and the sled, I believe, at a constant rate. She pulls with a force of 250 newtons, 40 degrees above the horizontal. How much work does friction do, and how much work does gravity do, right? So that means we need to know the force of friction. So I'll draw a little free body diagram. Since this often comes up and just looking at a lot of student work, remember, a free body diagram, a box, it can be a circle or something, but do remember, like, give me something that I can actually see, oh, there's the object that you're drawing, right? And then ideally draw the forces from the center. You don't always have to. I'm usually not really picky about that, but it can really help, particularly when you're trying to break them into components, right? So here I would look at this and say, well, as always, I probably have, right? See, I even try to make a little dot in the center. So I'm going to draw my forces from the center. If there's two going parallel, I'll separate them a bit, but just try to be careful with stuff like that, so you're communicating what you're actually want to communicate, and people can see it and understand it. So here I've got some gravity. So this is the force of gravity. So this box of mine represents the boy and the sled. And then we've got the normal force up. And then we're going to have an applied force. And we know that this is equal to 250 newtons. Fg, of course, would just be mg, and the normal force would respond to that. And friction will be in the negative direction. Okay. I'm guessing this thing's moving, so it will actually be kinetic friction, but for our purposes, I don't think it really matters. This one's a bit different. I guess I was a little off. There's a little bit of information missing from this, so we'll just kind of go with consider some distance delta d here, right? It doesn't really, we need a distance if we're going to figure out work. So I guess here I would just say, right, consider, all right, I'll just say that, consider a distance d, right? We'll just leave it as d and go from there. So I guess here what I would do is, well, let's break this up because we're going to need to. This here is a 40-degree angle. And so that means we can break the applied force up into its components. That means this here is going to be 250 sine 40. And this here is going to be 250 cos 40. And so if we sum the forces in the x direction, that's going to equal ma. Now we know this is happening at a constant rate, so I can just say that equals 0. And so looking in here, I've got the force of friction. I'll say that's in the negative direction. Let's just indicate my coordinate system here. Always good to do. So I've got minus the force of friction plus 250 cos 40 degrees equals 0, which just means the force of friction, if I take that to the other side, that would make it positive, is just equal to 250 cos 40, which I can work out, which is 191.5 newtons. So now if I want to do part A, I can say, well, the work done by friction and some distance delta d. Now here's where it actually matters that it is in the negative. When I did this equation up above, I said, look, I know friction is in the negative direction, so I just put in minus that, but it is very important that it is against the direction of motion, so I actually have to respect that sign again in my equation, and I have to say, well, it's negative 191.5 times whatever distance, so I'll just leave it as d, right? So whatever that distance happens to be, that's what it's going to be. I don't want to forget my units. This is going to be in joules. Or if I could leave this as, so basically this is negative 191.5 joules per meter. really, but I'll leave the D there that way. So if we go to part B for this, we want to know what is the work done by gravity. Right? Well, if you look at the situation here, this thing is moving horizontally, right? So it's not moving in the up or down direction at all. The force of gravity is completely in the like negative y direction. So since, right, we can say delta dy equals 0, therefore the work of gravity equals 0, right? Doesn't do any work. It certainly applies a force, but it doesn't do any work. Kinetic energy, the second part of today. You probably remember the equation. I'll write it as E with a subscript K. Some people might just write K or something, but I'll leave it this way, kind of follow the convention of the textbook. Also, a scalar quantity. And that's one of the reasons we often like to solve problems using, work and energy, because they're scalars. They're just a little bit easier to use. You don't have to break everything into components other than, like I said, what we just did to figure out the component of the force. But generally, it's, plug and play. The unit is the same. It's the joule. You can look at that a bit more specifically if you want. Remember, a joule is a Newton meter, if you will, right? So it's the same units as a Newton, which would be kilogram meter per second squared times by another meter. But since we're looking at kinetic energy and its equation, right, mv squared, you can see that, well, that also works out to mass, or kilogram times meter per second squared. But also a good reminder that when you're using this, you want things as kilograms and as, meters and seconds. That's about it. Just kind of a review of that. Now, the Work-Energy Theorem, right? This says that the work done on a closed system equals the change in the energy of the system. In other words, if you do some work on a system, right, you've got a mass just moving, like the boy is maybe sitting on the sled, maybe even going at some speed, it doesn't matter, right? If you do work like the sister in the last question on that, you change the energy of that system. Although I wrote a whole example here, so let me just read it. The total kinetic energy of all the air molecules in a sealed container cannot change on its own, right? If you have a container, maybe just picture like a glass container with a bunch of air molecules in it, that energy remains constant. And we're being a little bit simple in this. We're saying, look, that's like a closed system. It's isolated. Maybe it's like vacuum in a vacuum room or something. So we're not allowing for energy to go in or out of that system, which is not really practical. It will, but just for something to picture in your mind. So the energy of the individual molecules in this container may change from collision to collision, but the total energy of that system remains unchanged, right? They're just, when they hit, one may give the other more energy and may almost, remain relatively stationary, but nothing changes. If work is done, so maybe you heat this whole system, right, and the container is heated, the total energy of the system will increase. However, if the container is placed in a cold environment, the system would lose energy, right? So in that case, you could say the system would be doing work on its surroundings, right? It would be giving energy to the surroundings by heating the molecules around them. Right? So we have a sign convention here. Important to remember this when you're doing problems like this, because it really does matter. So we say that positive work is work done on the system. Right? So go back to the boy on the sled or whatever. If some external actor, the sister or you, anybody pushes them, you're doing work. That's positive work. However, we say that negative work is work that is done by the system, right? So if the boy crashes into something or whatever and ends up moving them as a result and slows down, right, then we would say that was negative work, right? Which should make some sense, right? The boy would have lost energy. Alright, I have an example for this. We have a child riding their bicycle. So the combined mass, so this is the mass of the child and the bicycle going 5 meters per second. They stop pedaling and you push them doing 2,000 joules of work. What is the child's final velocity? Right. And so here's the equation that we absolutely want, right? The work done equals the change in energy. So that's what we can look at here. We can say whatever work we did must equal delta E. And in this case, it's all just kinetic energy, right? The child had kinetic energy, they have more kinetic energy now. So we can also write that as work equals delta EK is just EK2 minus EK1. We know that initially the child is going 5 meters per second and the combined mass is 60, so we can figure out EK1. And we know that we did 2,000 joules of work in pushing this child to go faster. So we can just put all that right into the equation. We can say 2,000 equals EK2, which is what we want, or part of what we want, minus EK1, which is 1/2 times the mass, which is 60, times by the initial speed, which was 5 squared. And if we put in we can actually put in more numbers than that. Let me move this a little bit. We actually want EK2, so I can write that as 1/2 mv2 squared. Because really that's the only thing I want. I want V2, so I might as well just put it all into an equation like this. I can multiply everything by 2, which cancels those out. Oh, I should have written this as 60, since I know the actual mass. And that means I've got 4,000 equals 60 V2 squared minus so then I would add 1,500 to both sides, which means I've got 5,500 equals 60 V2 squared. Divide both sides by 60 and then take this square root of both sides, which will give me V2 equals 9.57. And I can of course check, does this sort of make sense? Well, yeah, the child was going 5 meters per second to start. Added some energy by pushing, and now the child's going almost double that speed. So yeah, that works.